Yep. Let's see if we can't have some fun. Last time we got a nice little relationship for drift velocity. So we got that relationship. Eventually, yes. Depends on how I write the problem. Now, the question is how can we know which direction drift velocity will be in? Drift velocity will be in the direction so it's going to be in a direction perpendicular to both the electric and magnetic fields. Okay, so the way we're going to look at this is we're going to start with what force is this? Nope. Nope. We said it last time. Whose force, like what force is this?
Oh.
The what? It's the Lorentz force. Lorenzo. Actually, I'd probably give you at least a few points if you said the Lorenzo force. It's close. Although Lorenzo's Italian, Lorentz is German, but that's okay. You just the structure of the name. My last name?
What? No, like.
It doesn't tell you anything about me because it's an origin of Old French. Nope.
No.
Because my dad married my mother and adopted me, so I have his name. Yeah. So by blood, honestly, I took one of those DNA tests. You know how most people are like a little bit of this, a little bit of that, a little bit of that. I was literally like half and half. Irish and Old Norse. In particular, Norwegian. But they used to just all be Norse. Pretty much. So we start with the Lorentz force. So our total velocity can be split into two parts. D is our drift velocity. What's the other force? What's another force that's going to be playing on this particle that could represent G? Mm-hmm. What's that second velocity? Gravitational velocity. Huh? That's not good. You're gonna need like, you ever seen the glasses that have like bottle glass on them? Like you're gonna need those. Like, like people will look at you and your eyes will be like this big.
Oh. No, no. I was close. I wrote you
Hey,
my driver's license. That's not that hard. You know, I have like, guys, if I split, I can make out like where I'm going.
well, you're not supposed to have to squint to see where you're going. No, most people don't have to squint to see where they're going. What? Get all of you get glasses. Don't wear them. Yeah, I know.
Oh my God. I tried to run. Yeah, I said that it was, I think that's how. Because some people like, if they're allergic to hair, so you will go carrot, you will go carrot, and then eventually you eat carrot. Yeah, Jane is gonna do with me next time.
Oh, look, there goes my eye twitch. Okay.
No. Yeah, you, I don't know where that's coming from, maybe it's. Yeah, maybe.
So, do we no, that's not going to happen. Do we remember how to add vectors? Yep. So, no, you better be freaking joking. Great. That means the forces of evil are now loosed upon us. Chuck Norris was holding all the evil back. That was.
$1. That'd be so lit. I have been $5.
I know, they're so expensive.
The best. How do you know that? You guys.
Oh yeah. We're doing Z. Because this whole thing of you guys existing in a two-dimensional world's got to come to an end. No. Let's try to step things up instead of you all having one-dimensional relationships and two-dimensional physics. Let's step everything up a level. I'm going to let you work on that one for a while. So another way we can represent this is through Dirac notation. See, we can finally use Dirac notation because we're actually using matrices. No. No. Okay, now what we're going to do. Yeah, let's use the better notation. Yep. So that's Dirac-Brocket notation.
What?
It's Dirac-Brocket notation.
Plays a lot.
You can't put your down. Go up.
Oh, there's the brain pain. There's the brain pain.
I rated that. No, I don't think that's the bad.
So this type of notation is usually used when you're working with matrix vectors. Oopsies. Be proud that what? Yes. Well, like, what are you talking about? You could, yeah. Yeah. So determinant that's a little bit larger than what we've been doing. Okay, so that's going to give us and you guys get the pluses and minus based off the parity operator, right? Just add together the number of the row and the column. If it's even, it's a plus. If it's odd, it's a minus. And we'll just leave the parity operator out of it because it just makes it look worse, but the parity operator just boils down to a plus or a minus one. And then once we have our 2x2s, what do we do? Yeah, but what process do we use? The determinant of a 2x2 matrix, or what's the procedure? I saw the assignments. A lot of you did it correctly.
Cross together. It's like you like.
Yeah, you cross multiply and you subtract. Oh, okay. Well, you butterfly it. Okay, so our I hat Mhm. Well, because you have the four terms in the 2x2 matrix. I'm going to multiply that way first. And then I multiply that way, and I get two numbers and I subtract.
Okay.
It's
I
a,
just need to know that.
yeah, you cross multiply and subtract. And why do we have to extend to the Z axis to do this properly or to do it at all? Well, that is true, but so if I had vectors at only X and Y, then my determinant would be I and J, and then the two vectors, which would be a 3x2 matrix. And can I take the determinant of a 3x2 matrix? Absolutely not. To take the determinant, you have to have a square matrix. What do I mean by square? Yeah, so it has to be 3x3, 4x4, 2x2. But if I want to when we get there, you're going to see this process done again. You're going to show how instead of having to use the right-hand rule and guess which way a force is pointed, the cross product will give you a vector in exactly the right direction. So we have this. So let's look at the cross products of a separated. So let's do that. When you work this out, what you're going to get, yeah, you get that once you work it all the way out. Then we want to look at the gravitational velocity. That is going to end up giving us Okay, so we have those two separated out. Now let's take this vector up here. And let's go ahead and distribute those magnetic fields in. Yeah, actually. So what we're going to end up getting and again, if that's confusing, you want to go all the way back up to here. You want to multiply in those b's and then move everything around into single terms, and you'll end up here. Now let's separate terms. I'm going to separate drift velocity and gravitational velocity terms. Yep. See, I just multiplied in the magnetic field terms and then moved them around to have plus, plus, minus, minus. Oh, yeah. Then what you notice, so when we did these individual ones here, the drift velocity cross B and the gravitational velocity cross B, what you notice is now each one of our terms We have our x components. Our y components, and of course, these are our z components. Which means the cross product we started with will end up becoming which means the cross product is distributive. Okay, now we're going to go back to our original differential equation, our Lorentz force, and it's going to now look like this. Now, we need to do some comparison. So first off, look at that derivative. What's another way I can write that that's going to help me do some comparison? Yeah, do derivatives distribute? Yep. So this is going to end up becoming so that's going to be helpful. And then we want to study this for a steady drift velocity. A steady drift velocity, what does that mean? It's the same all the way through, which means, so there is no what? No acceleration. And one thing you'll find out, this is called a critical point. And in calculus, a critical point means your derivative equals 0. So let's write okay, so now we're going to have going to separate this a little further. Perhaps you should keep your hands to yourself. Okay, so now we're separating that a bit further. So now by comparison, we can separate out the terms that are the individual differential equations for each type of velocity. So if I'm looking at And keep in mind, the gravitational velocity doesn't just disappear, but we're worried about the drift velocity of the particles inside of a conductor. So we're picking that out. What does this equal? Eventually, yes, but if you're going to curse, do it right. Okay, so we can divide the Q out. So now what we want to do is, remember we started by saying that drift velocity is in the direction of E cross B. So now we want to cross B into both of these. So now the next thing I'm going to give you, take this as an identity. Now, technically with the stuff, you could prove this. However, that would be a homework assignment that would take like 15 to 20 pages. But so just take, take this as an identity, okay? That's why I'm saying that's why I'm saying I'm not giving it to you. I just know there's always going to be someone that goes, how do you know that? Well, guess what you're doing on your assignment now. Okay, so
I just. Everyone told me this is what this means, and I say, okay.
that's a dot. You can never just multiply vectors. You have to have a dot or a cross. It has to produce either a scalar or a vector. But like I said, we could get further in using matrices. We could do wedge products and inner products and outer products. And did you ever figure out that wedge product?
No.
You looked it up and went, absolutely not. Okay, so we're going to do that to this side here. So that means our E cross B is going to equal the negative. I don't think we have to prove that anymore. We've already done that. Now, what angle do we find between the drift velocity of the magnetic field? What angle do we find between the drift velocity and the magnetic field? We've been talking about it, 90 degrees. Drift velocity and magnetic field are perpendicular to one another. So that means our B so that whole thing equals 0. So that means that our drift velocity and so we said that originally the drift velocity is going to be in the direction of the E cross V vector, E cross B vector. So what you have here is a direct proportionality, well, yeah, we could call it a direct proportionality between drift velocity and the E cross B vector, which means that two vectors that equal each other, just whole number multiples of each other, are going in the same direction. So when you have two vectors that, I mean, they essentially equal each other. They're just a numerical multiple of each other. They're going in the same direction. So it's like if I have vector A and then vector B is just 2 times A, I mean, it's still A, it's just twice as big. So it's still going in the same direction. So you're able to actually see that this drift velocity is going to be in the same direction as that E cross B, which is your textbook just expects you to accept that for no reason at all. It's no, that's not the only reason. Yes. Okay. Oh, I gave myself more space than I really needed. Okay. Quentin be squinting. So now we're on to something called the Hall effect. Nope. So imagine you have a current carrying chunk of chunk of material. When you put that material into a magnetic field perpendicular to the current, what starts happening is the charges inside that material are going to deflect to one side of that material. And you're going to get now you'll have a potential difference across that material. You're going to get to the point where the electric force and the magnetic force equal each other and the current just starts going regularly. So you get a maximum potential difference. One of the reasons this is important is a lot of sensors are set up this way. They will use things like the Hall effect to judge certain physical reality inside the system. So like how much of that Hall potential did you actually get?
Oh my God, that's
What's IS? So that's the field.
Yep.
The VH.
That's your Hall potential. Okay. Flat slab of semiconductor has a thickness of 0.5 millimeters, width of 1 centimeter, and length of 30 centimeters. Current of 2 amps flows along its length to the right. A magnetic field of a magnitude 0.25 Tesla is directed into the page, perpendicular to the flat surface of the slab. Assume the charge carriers are particles with charge positive E. So that makes them what? What is the charge carrier with positive E? Nope. Well, yes, actually, but so I guess that's not a fair question. Which matter particle is a positive E?
The thing on the assignment.
Nope, that's the positron, that's antimatter. Protons. Protons are the matter version of positive E.
Is there a negative proton?
Yep,
That-
I need to look that up again. And the positron is the anti-electron. Yeah, see, the transformers keep coming into my head. The negatron. No, it's not. It's not. It's not. Okay. There are 7.0 times 10 to the 24th mobile charge carriers per cubic meter. What is the magnitude of the Hall voltage across the slab? Oh yeah, antiproton. Okay. Well, there's a couple of things we need to go through to solve this. So the first thing we're going to need is an expression for our drift velocity.
What's in that? One over V squared.
Yeah, we're going to do this a little different. Who remembers this equation?
That's what I was thinking of. I don't know why I thought it was a bird.
Okay, well, we will continue with this on Monday.
What's the peanut guy say? Is that the same guy that you're talking about?
Oh, yeah.
Brandon,